So in your mathematical career so far, or in your classes, when you talked about something being continuous, you might have described it as um, a graph that you could draw without picking up your pencil. If you had to pick up your pencil somewhere when you were drawing that graph and it wasn't continuous there. Well, that's kind of an intuitive what's going on if it's not continuous at a value. But we want to show mathematically, and now you're going to have you have the tools to do that with limits to see if it's continuous at some value x equals a. So we say a function is continuous at x equals a if and only if so this means this has to hold true. Everything has to hold true. Mathematically, you might learn later on when your teachers or your teacher might do IFF. That means if and only if. If and only if the following hold. So it actually has to exist at x equals a. So f of a exists. So recall, we saw that limits, we could have a limit at x equals a even if it didn't exist. We could be approaching the same y value, but in order for it to be continuous, it has to exist. The limit as x approaches a of f of x has to exist. And so recall the stipulation: in order for a limit to exist, we need to show that the left-hand side and the right-hand side. So limit as x approaches a on the left is equal to limit as x approaches a on the right. So the limit exists, plus that limit when it exists. So limit as x approaches a of f of x. This is just f of a. So doing our direct substitution. So if all three of those things occur, then we can say that a function is continuous at that value x equals a. So let's look at what the scenarios are, or cases that could be where x is not continuous at x equals a. And if it's not continuous, we say it's discontinuous. And then there's three, actually there might be more than three now for your class. I was teaching this today in Math 9 also. So you guys, some of these videos that I'm creating, you can also watch my Math 9 videos. They're not going to have trig in them, and I'm trying to do different examples for both of the courses. I might not have started out that way at the beginning of the semester, but if you wanted to watch more videos on certain problems that you're doing in this class, you could watch my Math 9 videos. Okay. So not continuous at x equals a, then it's discontinuous. Darn it. And there's different types of discontinuity. So one of them would be if we had some sort of jump in the graph, where you might have some function here. So the limit in this case, there's a jump. So that jump in the graph shows us that the limit here is x is approaching a on the left. Maybe we can say that's L. And this does not equal the limit as x approaches a from the right of f of x. Which, let's say maybe that's a y value of m. Okay, so a jump in the graph. This is what's going to occur. We may have an asymptote, vertical asymptotes. So recall vertical asymptotes happen when we have a rational function, and those are values which set our denominator equals 0 and not our numerator. We'll talk about this more next week about asymptotes, vertical asymptotes. But for now, maybe we have this value x equals a. Recall we did for asymptotes, we denote it by a dotted line. And so we might have something where x is coming in and from the left and it's shooting off to positive infinity. It's possible that coming in on the right, it's also going up to positive infinity, or it could be shooting down. But if it's going to positive infinity or negative infinity as we're coming in on the left or the right, then it's an asymptote and the limit doesn't exist. And it's discontinuous there. But technically, those could be plus or minus. I'm trying to think of the other. Oh, and there's one other type. So recall, we could have a graph, right, where there was an open circle at x equals a, but the limit exists, right? As we got closer and closer to a on the left and on the right, we still got the same y value. But in this case, the limit as x approaches a exists is equal to L, but the condition that doesn't hold, it's not defined at f of a. It's either not defined there or what if we had a point up here, right? We could have a solid circle there. Or if it's defined, at x equals a, that limit as x approaches a of f of x does not equal f of a.